Okay, in today's lecture, we're going to cover the second part of the section 1.1 material on linear systems. And in the first part of our lecture, we had discussed a algorithm or some process for solving systems of linear equations, which was known as Gaussian elimination. The process of Gaussian elimination is used to solve linear systems by performing one of three elementary operations on our system to obtain an equivalent system which is easier to solve. And recall that an equivalent system is one which has the same solution set as our given system. So in the first part of that section, we had looked at applying Gaussian elimination for systems of three linear equations in terms of three variables. And we saw that it can be a little bit tedious to write out our work when we're performing Gaussian elimination. So in this second part of the section, we're going to make use of matrices to simplify our work in solving a linear system. So let's start with a little bit of notation. So starting with the definition, we would say that a matrix is any rectangular array of numbers. Usually written in either parentheses or brackets. In your textbook, they use a bracket notation, so that's what I'll use in the lecture notes. But typically when I write matrices by hand, I prefer to use parentheses. So throughout our course, when you see me write matrices, I'll use parentheses instead of brackets in most cases. Now, the notation that we're going to use for matrices in our course is a capital variable. So say the capital letter A would be used to denote a matrix A. And we see here that we have some rectangular array of numbers written in square brackets. So here we have a matrix where these numbers, denoted as A sub ij, are called the elements or entries of our matrix. So we can see here the elements or entries in our first row of this matrix are denoted as A11, A12, up through A1n. So here we have a matrix with n columns. And the first subscript in the first variable in our subscript, aij, tells us which row that we're lying in. So here we have A11 for the first row, first column entry, A21 for the second row, first column, A22 for the second row, second column, up through A2n for the second row, nth column. Down through some A sub m1 for the entry in our mth row first column, AM2 for the mth row second column, up through AMN for that last entry. So when we refer to the dimensions of a matrix, we're asking how many rows or columns it has. Some people say size of a matrix, some people say dimensions. So the dimensions of a matrix are indicating how many rows and columns are in that matrix. So in this general definition that I've given, we had a matrix that had m rows and n columns. So any matrix with m rows and n columns is said to be an m by n matrix. So when we are referring to the dimensions, the first dimension, m, is the number of rows, times n, the number of columns of that matrix. Now, in the special case that we have the same number of rows and columns, our matrix is said to be a square matrix. So that would be some n by n matrix that has the same number of rows as columns. And in some special cases that we'll consider throughout the course, we'll work with a matrix that has only a single row or a single column. And any matrix that consists of a single row or a single column is sometimes called a vector. You might have seen vectors in your calculus courses before. So in particular, we would say that a column vector is an n by 1 matrix that has a single column. So n rows by 1 column would be a column vector. And similarly, a row vector would be a 1 by n matrix that has a single row and however many columns. So when we are talking about solving linear systems, we can write all of the essential information for our linear system more compactly by using a matrix. So let's consider a general system of linear equations, say in the variables x1, x2, up through xn. And altogether we have m equations. So in our first equation, this linear combination of x1 through xn is equal to b1. For our second equation, we have this linear combination is equal to b2 down through bm. So we have altogether m equations in terms of n variables, x1, x2, up through xn. So for such a linear system, we can define what is called the coefficient matrix of that system, and the column vector for the right-hand side of that system as follows. So the coefficient matrix would be denoted as capital A, and the entries of this coefficient matrix consist of the coefficients of our variables x1 through xn for each equation. So to look at this a little more specifically, in our first equation, the coefficient for x1 was a11. So that would be the entry of our first row and first column for the coefficient matrix. In that first equation, the coefficient for x2 was a12. So we would write that as our first row, second column entry. Up through, we had n variables, so our coefficient we could denote as a sub 1n for our entry in the first row and nth column of our coefficient matrix. Then for the second row, well, it works similarly. The coefficient for x1 was a21, so we put that coefficient as the second row, first column. a22 would be the second row, second column, up through a2n. And then moving downward through our last equation, let's say we have m equations all together. The coefficient of x1 in that last equation was am1. Coefficient for x2 is am2 up through amn. So these coefficients for our variables, if we write them in the rows and columns of a matrix, we have what is called the coefficient matrix for that system. Now we can also denote a column vector. We could call this the column vector for the right-hand sides of our equation. And we could denote this as a column vector b, which would be the m by 1 column vector, whose entries consist of the constants on the right-hand side of our equation, b1, b2, up through bm. So our linear system that we're considering here can be described by using what is called an augmented matrix. So what is an augmented matrix? Well, it is a way to combine multiple matrices into a single matrix. So there's a couple of ways that we could write this augmented matrix. The first of which would be in the following way. So our coefficient matrix A, which was an m by n matrix, we could copy the entries of that matrix and then use a vertical bar, and on the right-hand side of that vertical bar, we would have our column vector B, consisting of the constants b1, b2, up through bn. Now this is my preferred notation for the augmented matrix for a linear system, and this is what you'll see in most mathematics, engineering, and physics textbooks. The textbook that we're using at UTSA for this course uses a slightly different notation. They just omit the vertical bar between your coefficient matrix A and the column vector b1 through bm. So rather than using that vertical bar, they just omit it there. So just a word of warning, when you're working on homework problems or looking at problems in the textbook, they will not use that vertical bar, but in my solutions, I'll typically write that vertical bar in place we'll see why that vertical bar notation might be a little clearer or a little more beneficial as we work through our course. So now that we've introduced this terminology for matrices and defined a coefficient matrix for a system and seen that we can express a system in terms of an augmented matrix, let's think about how we can solve linear systems by making use of these matrices. So in order to solve a linear system, we saw in the last part of our lecture that we could perform Gaussian elimination on the equations in our system to get an equivalent system that's a little simpler. So now that we know that we can express a system in terms of a matrix, we could simply express our system in terms of an augmented matrix and then perform Gaussian elimination on the rows of our matrix, because each row of this augmented matrix corresponds to an equation in our system, and we're wanting to perform Gaussian elimination on that system of equations. So what are the operations that we can perform on an augmented matrix? Well, initially we had called them elementary operations. Now that we're expressing systems in terms of matrices, we would call these elementary row operations, since each row is an equation. And so we had 3 elementary operations that we could perform. The first is that we are allowed to multiply any row by any non-zero scalar, any non-zero number that I want. We can replace any row by the sum or difference of itself and a multiple of another row. So I can multiply any row by a positive or negative constant and add it to another row. So equivalently, I can add or subtract constant multiples of any 2 rows. And our last operation that we discussed is we can interchange any 2 equations. So when we're expressing them as augmented matrices, this means that we could interchange any 2 rows. And the augmented matrix that we're left with represents a system which is equivalent to the given system. So let's look at some examples making use of these augmented matrices to solve linear systems. In our first example, we are asked to solve the following linear system. So we have 3 equations here in terms of the 3 variables, x1, x2, and x3. So again, we could think about this geometrically as representing 3 planes in space, x1, x2, x3 space. And we're trying to find the points, x1, x2, x3, that would lie on all 3 of these planes. So let's see if we could use an augmented matrix to solve the system instead of just using Gaussian elimination as we did in the first part of our lecture. So our first step here would be to rewrite this system in terms of an augmented matrix. So the entries in the first row of our matrix are going to be the coefficients of x1, x2, and x3 in our first equation. So for our first equation, we had 1x1 plus 2x2 minus 3x3. So our first row would consist of 1, 2, negative 3. And then that was equal to 9. So our last entry in that first row would be 9. And my personal preference would be to separate those entries by a vertical bar. I can think about this vertical bar as representing the equals through my equation. And each of these columns is the coefficient for my variable, x1, x2, x3, and some constant b. So let's keep writing out our system. We have, for our second equation, 2x1 plus x2 minus x3 is equal to 5. So those coefficients will go in the second row of our augmented matrix. Here we'll have 2x1 plus 1x2 minus 1x3 is equal to 5. And in our last equation, we had 4x1 minus 3x2 plus 5x3 is equal to negative 9. So writing in those coefficients for our third row, we have 4, negative 3, 5, and negative 9. So our goal is to perform Gaussian elimination on the rows of this matrix in order to have a simpler matrix for an equivalent system. So we're going to perform Gaussian elimination on the rows of our matrix, and the procedure that we're going to use to simplify here is similar to what we had seen in our earlier examples from the first part of our lecture. So for instance, I could maybe try to kill off one of my variables in two of my equations. So for instance, if I wanted to kill off the variable x1 in my second two equations, I want to take this coefficient of 2 and 4, x1, and transform them into zeros. I want 0 x1 in each of those two equations. So let's think about how we could do that. So to get rid of the 2x1 in our second equation, I could use the coefficient of 1x1 in my first row. So I could, one way that I could do this would be to take my first row, multiply through by negative 2, and add it to the second row. Or equivalently, take row 2 minus 2 times row 1. So the notation that we'll use for Gaussian elimination on augmented matrices is similar to what we saw earlier. We would say that this augmented matrix is equivalent to the matrix that we would get by performing the following row operation. I'm taking row 2, so I'm going to denote it as R2, maybe instead of E2 since I'm no longer working with equations. And I'm going to subtract 2 times R1. So my first row I'm leaving alone. I still have the entries 1, 2, negative 3, and 9. And when I perform this operation, let's see what we have. So taking a negative 2 times my first row, I get negative 2, and then I'm adding it to the row below it. So my negative 2 plus 2 gives me a 0 entry here. Taking negative 2 times 2, we have negative 4, and I'm adding that to a positive 1, so that gives me negative 3. Then taking a negative 2 times the negative 3 in my first row, we have a positive 6. Adding that to a negative 1 gives me a positive 5. And then performing that same operation on the right-hand side of our equation, we have negative 2 times 9 would be negative 18 plus 5 leaves us with negative 13. Now, in this same step of Gaussian elimination, I want to try to eliminate the x1 variable in my last equation, that is the third row. So to eliminate that constant of 4 and turn it into a 0, well, there's a couple of ways I could do it. One way would be to take negative 4 times my first row and add it to the third row, sort of similar to what we had done in our earlier examples. Or another way I could do this, I see that my second row had a coefficient of 2, so I could take the second row, multiply by negative 2 to get a negative 4 value there, and then add it to that third row. So here again, I'm illustrating that there's more than one way that we could perform Gaussian elimination to get our solution, which is why whenever you're writing out your solutions, you always want to indicate what row operations you're performing from one step to the next. So just to illustrate that there might be alternative techniques to obtain your solution, let me go with that second option, where I'm going to take my third row, row 3, and subtract from it twice row 2 instead of making use of that first row. So let's see what we get here. So we would have a negative 4x1 plus 4x1 in my third row, gives me a 0. In the x2 coefficient, I would multiply my second row by negative 2 to get negative 2 and add to negative 3, so that gives me negative 5 for my x2 coefficient. And for our x3 coefficient, I've got a negative 1. If I multiply by negative 2, I have positive 2 plus 5, which gives me a value of 7 there. And then performing the same operation on the right-hand side, multiplying second row by negative 2, I have negative 10 plus negative 9 gives us a negative 19. So we've got an augmented matrix, which is a little simpler than the one we started with. And if we want to go ahead and solve this system, well, we need to eliminate one of the variables, either x2 or x3, from my last two equations. My last two rows now only involve the two variables x2 and x3, so I want to try to get rid of one of them. Now we see in this example that it's a little bit tricky. We could try to kill off the x2 variable by comparing the coefficients for x2 in that second and third row, but we see that negative 5 is not an integer multiple of negative 3. If we tried to kill off x3, we see, well, 5 and 7 are not integer multiples of each other. So we could introduce fractions here, maybe take my second row, multiply by a negative 5/3 to get a positive 5, and then add it to the third row. But typically we try to avoid fractions when possible. So another way that I could proceed here would be to just simplify the coefficient of x2 in that last equation a little bit. So one way that I could maybe just reduce the size of this x2 coefficient in my third equation would be to subtract the row before it. So in my next step, I would take row 3 and subtract row 2 from it. Now again, if you're working this problem on your own, you might say, well, how would I know to do that? Well, you don't have to. There's a number of ways that you could go about solving this system. You could take that fractional power of your second row and add it to the third row to kill off x2 directly in this step. But my own preference would be to avoid fractions. So let's see what this would leave us. We have our first row is still the same, 1, 2, negative 3, positive 9. Our second row, we're leaving alone for now. We have 0, negative 3, 5, and negative 13. And if I was taking row 3 and subtracting row 2, let's see what we have. We have, for our x1 coefficient, 0 minus 0, which is 0. For our x2 coefficient, we have a negative 5 minus a negative 3, or plus 3, would leave us with negative 2. And for our x3 coefficient, we have 7 minus 5, which leaves us a coefficient of 2. And then doing the same operation on our right-hand side, we have a negative 19 minus a negative 13, or plus 13, would leave us with a negative 6. So from here, there's a few ways that we could proceed. One thing that I notice when I might try to simplify here is that every entry, or every element in my third row, is even. So I could divide everything through by 2 to simplify the entries in that last row. So one way I could proceed would be to take half of my third row, or I might prefer to make my lead coefficient a positive 1 instead of a negative 1. So rather than dividing through by 2, I might divide through by negative 2, or take negative 1/2 of my third row. So that makes my third row a 0, positive 1, negative 1 is equal to positive 3. Now, if you just divided through by 1/2 in your own solution, you would have 0, negative 1, positive 1, negative 3 for your last row, but our systems would still be equivalent. Now, my first row, I'm not going to manipulate. So here I would have 1, 2, negative 3, and 9. And in this same step, one thing I might do if I want to have a coefficient of 1, x2 in my second row, let's think about how we could get a 1 there. Now, one way would be to, say, divide everything through by negative 3, but again, since our second entries are 5 and negative 13, we may not want to introduce fractions there if they're not multiples of 3. But another way that I could get a 1 coefficient in that second row would be to subtract row 3 from row 2. So that is, in this same step, I'm also going to take row 2 and subtract row 3 from it. So let's see what that gives us. We have 0 minus 0 gives us a 0x1. We also have, for our second coefficient, a negative 3 minus a negative 2, or plus 2, gives us a negative 1. For our x3 coefficient, we have 5 minus 2, which leaves us with 3. And then subtracting our constants, we have a negative 13 minus the negative 6, or plus 6, would leave us with a negative 7. So at this stage, by performing these operations, I now have, for my second two rows, a coefficient of x2 and a negative 1, and a coefficient of x2 of positive 1 in those second and third rows. So now it becomes much simpler to kill off one of those x2 coefficients without having to use fractions. So one easy way that I could proceed would be to take row 3 and add row 2 to it. So my first row is still the same. I have 1, 2, negative 3, 9. And in our second row, we have 0, negative 1, positive 3, negative 7. And in our third row, if we add the previous row to it, we would have 0, 0, 2, and negative 4. So at this stage, I see, I can divide my last row through by 2, since all of the entries in that last row are even, and I would have this is equivalent to the matrix. Or my first row, I'm going to leave alone. I've got 1, 2, negative 3, 9. For my second row, I have 0, negative 1, 3, negative 7. And taking half of row 3, I have 0, 0, 1, negative 2. So once we have our matrix in this form, we can find our solution, or we've got our solution from here. Let's think about what the rows of this matrix represent again. Remember, these are just equations where the columns are the coefficients for x1, x2, and x3 in each equation, and the right-hand side is this column vector of constants b. So what our last equation says here is that 1x3 is equal to -2, or in other words, x3 we find is immediately -2. Now, if we know x3, we still need to find x1 and x2. And to find x2, I could substitute into the previous equation. My second equation gives a relationship between x2 and x3 only, since our coefficient for x1 was 0 in that row. So let's look at what that second row says in equation form. It says -x2 plus 3x3 is equal to -7. So if we know x3 is equal to -2, we have -x2 minus 6 is equal to -7. So -x2 is equal to -1, and x2 is 1. And to find x1, we could back substitute the values for x2 and x3 into our first equation. So looking at the first row of our matrix here, we have the equation 1x1 plus 2x2 minus 3x3 is equal to 9. So substituting in the values that we've already found for x2 and x3, we have the following. We've got x1 plus 2 times x2, which was 1, minus 3 times x3, so that gives us a positive 6 is equal to 9. So x1 plus 8 is 9, and x1 is then 1. So in this example, we obtain one solution. So here we could say there is only one solution, namely the point x1, x2, x3 is equal to 1, 1, -2. So we obtain the following point as our solution. So geometrically, we could think about this point as being the point of intersection of the three planes that were described by the equations given in our problem here. And one way that we can always check our answers for these linear systems is to take the point that we found, 1, 1, -2, and substitute those values in for x1, x2, and x3 in our earlier equations and see if all three equations hold true. So here, if we were to substitute those values in for our variables, we see that all three equations do indeed hold, so we have found one possible solution here. And in this case, this is the only solution. We obtain the following by performing Gaussian elimination on our augmented matrix. And once we got it down to a simplified form, we could solve for one of our variables and then back substitute into the earlier equations or earlier rows in order to get the values for x1 or x2. Now, there is another way that we could have proceeded here instead of using that back substitution approach. So to illustrate another method that we could have performed, let's consider the following and see how we would get the same solution. So let me go back a little bit earlier in the problem. I'll erase the work that I've done in this last step, or last few steps. And let's see how we could have gotten that same solution directly from the augmented matrix if we had just performed a few more steps in our Gaussian elimination. So here, the matrix that I obtained to get my solution, if I simplify a bit further, I could say is equivalent to the matrix that we get by performing some other operations. So let's think about which operations I'm going to perform here. So if I want to avoid that back substitution part of my process, I could think about killing off the other variables x2 and x3 that appeared in the first or the second equation. So that is, if I were to make each of these coefficients for x2 and x3 in my earlier equation 0, then I get my solution directly from the matrix. Let's see how this works. So let's say, for instance, I wanted to kill off this positive 3 term that appears in the second row, third column. So one way I could do it would be to use my third row. I could multiply my third row by -3 and then add it to the row above it. So that is, take row 2 and subtract from it 3 times row 3. So let's see what this gives us. My last row I'm leaving alone. I have 0, 0, 1 is equal to -2. And if I perform this operation, let's see what that second row becomes. I have 0, -1. Then I'm multiplying my third row by -3. So I would have a -3, and then I'm adding it to the second row. So my -3 plus 3 becomes a 0. And then performing that same operation on our constants, multiplying -3 by -2, I have a +6. I'm adding it to -7. That leaves me with a -1 here. Now in that same step, let's say that I want to kill off the coefficient of -3 in that first row. So if I were to make use of this row below that, or my last row, I could multiply my last row by a +3 and add it to the first row. So that is, take row 1 and add to it 3 times row 3. So let's see what this gives us for our first row. So we would have a 1 plus 3 times 0 is still just 1. Then we would have a 2 plus 3 times 0, which is still 2. And then my 1 times a +3 adding to the -3 gives me a 0 for the x3 coefficient in my first equation. And performing that same operation on the constants, let's see what we get. So we would have 3 times -2 is -6 plus 9 gives us a +3. So to simplify just a bit further, I notice that in my second row, everything is a negative. I've got coefficients of -1. So if I want to get rid of the negatives on both sides of that equation, I could multiply my second row by -1. That is, just take the negative of row 2, which makes my second row 0, 1, 0, 1. My last row, I'm going to leave alone. I have 0, 0, 1, -2. And in my first row, I have a 1x1. And if I want to eliminate the coefficient of x2 in that first equation to avoid a back substitution, well, one way that I could do it would be to take this -1 coefficient from my second row, multiply it by 2, and add to my first row. So that is, take row 1 and add to it twice row 2. So that leaves us with a 1, Negative 2 plus 2 gives us 0, and then our 0 plus 0 is 0. Performing the same operation on the constants on the right-hand side, I would multiply my negative 1 by a 2, giving me negative 2. Adding to 3 gives me a value of 1. So looking at this final matrix that I've obtained, let's think about what these rows say in equation form. Remember that here my columns are just giving us the coefficients for x1, x2, and x3, and a constant. So my first equation here says 1x1 is equal to 1. In other words, x1 is 1. My second row says 1x2 is equal to 1. Or in other words, x2 is equal to 1. And my third row says 1x3 is equal to negative 2, or equivalently, x3 is equal to 2. So we have the same solution set that we did, that we obtained from our earlier work, where we didn't reduce our matrix completely, but we performed some back substitution steps. We have the point x1, x2, x3 is 1, 1, negative 2. x3 was negative 2 here. So we see that there were multiple approaches that we could use to get this same solution. In our initial approach, we had this matrix where we could read off one of the variables from our last row and then substitute into the earlier equations in order to obtain our solution. And there was nothing wrong with that. It just took a few extra steps in that back substitution to solve. But if we were to perform some more steps in Gaussian elimination, we get a simplified matrix from which we can read off our solution directly. So in this process of performing Gaussian elimination, we are trying to reduce our augmented matrix to this simplified form. Because we see here, if we obtain that simplified form, we get our solution immediately. So let's look at some other examples here. In our next one, again, we are asked to solve the following linear system. So we have, again, 3 linear equations in terms of 3 variables, x1, x2, and x3. So in order to solve this, we're going to perform Gaussian elimination on the rows of the augmented matrix for this system. So let's start by writing that matrix. In our first row, the coefficients for our variables are 1x1 plus 4x2 minus 3x3, and that was equal to negative 13. In our second row, we had a 2x1 minus 3x2 plus 5x3 is equal to 18. And in our third row, we had 3x1 plus 1x2 minus 2x3 is equal to 1. So we have the following matrix, and again, our goal here is to transform this coefficient matrix A into the form where we had 1 for the coefficients of x1, x2, and x3 in each of our 3 rows. And then we want zeros everywhere else for that augmented matrix. So let's see how we could get that. Usually the way that I prefer to proceed is moving through column by column, starting with my x1 column. So here, the column representing my coefficients for x1 is this first column, 1, 2, 3. And I already have this 1 coefficient that I want in the top left entry. Now, for the entries below that, I want both zeros. I need to kill off this 2 and 3 value. So to kill off the 2 in our second row, well, one way I could do it would be to take row 2 minus twice row 1. So I'm not changing my first row. I'm still going to have 1, 4, -3 is equal to -13. In my second row, let's see what we're left with. I'm multiplying the first row by -2, adding it to the second. So -2 plus 2 gives me a 0. Multiplying the first row by -2, I have -8 plus -3 leaves me a -11. And in my third row, I have, or my third column, multiplying -3 by -2, I have 6 plus 5 gives me a positive 11. And performing the same operation on the right-hand side, I have a -13 times -2 would be 26 plus a positive 18 leaves me with positive 44. Now in this same step, let me try to kill off the coefficient of 3 for x1 in that third row. So an easy way to do this here would be to take my third row and subtract from it 3 times the first row, or equivalently multiply row 1 by -3 and add it to the third row. So we would have a -3 plus 3 gives us 0. For our second column, we would multiply 4 by -3, so -12 plus 1 gives us a -11. And in our last column for that third row, we were taking a -3 multiplying by -3, so that gives us 9. Adding to our -2, we've got 9 minus 2 leaves us with a 7 here. And performing that same operation to our constants on the right-hand side, taking -3 times -13 is 39 plus 1 leaves us with 40. So now my first column for this augmented matrix, x1, has exactly the form that I want. Remember, I'm trying to reduce this to something of the form with 1s on these diagonal entries and 0s everywhere else. So my first column is exactly what I want. Now, in order to keep simplifying and change our second column, which is the coefficients for x2, into the form that we want, well, recall that we want to have a 1 for this diagonal spot. So there's a few ways that I could go about getting it here. One way would be to divide my second row through by -11. Notice that each of these elements in my second row is a multiple of 11. So I can divide through by 11 in order to simplify, and I'm not introducing any messy fractions here. So in my next step, I'm going to take -1/11 of my second row. So my first row I'm going to leave alone. We have 1, 4, -3 is equal to -13. Dividing my second row by -11, I have 0, +1, -1, -4. So that gives me that 1 element that I was looking for. Now, in this same step of the Gaussian elimination, I could keep simplifying. I know that ultimately I want this entry in the third row, which is currently a -11, to be 0. So one way to get a 0 there would be to take the second row that we had and subtract it from that third row. So that would give us, or the operation that I'm performing would be to take row 3 and subtract row 2 from it. So that gives me a third row of 0, -11 plus the 11 gives me a 0, x2 in my third row. And then I had 7 minus 11 will give me a negative 4. And then performing that same operation on the constants on the right-hand side, I have 40 minus 44 gives me a negative 4 there. So at this stage, we could solve for x1, x2, x3 directly, because looking at our last equation, we could immediately say that x3 is equal to 1 and then back substitute. But if we want to use Gaussian elimination to complete this process, we could keep moving and just read off our solution directly from the simplified matrix. So let's think about what else we're trying to do here. To get the form for the augmented matrix that I want this last entry in my third row to be a positive 1. So an easy way to get it here, if we notice that our constant on the right-hand side of the third equation is also negative 4, we could just divide through our third equation by negative 4. So let's see what that gives us. This is equivalent to this matrix we get by taking negative 1/4 of row 3, which makes my third row 0, 0, 1, 1. Now, in this same step, we could maybe simplify one of our other rows. So for right now, I'm going to leave my second row alone. Let's take it as 0, 1, negative 1, negative 4. But I noticed that one thing I could do in this same step of the problem is to kill off this positive 4 term in the second column of my first row. I know I want it to be a 0. So in order to get a 0 there, well, I could take my second row and multiply by negative 4 and add it to that first row. So that is take row 1 and subtract 4 times row 2. So let's see what that leaves us. We would have a constant 1 minus 4 times 0 is still 1. We would have a 4 plus our negative 4 leaves us the 0 that we wanted for that second column, first row. And then taking our second row times a negative 4, we have a positive 4 minus 3 leaves us with a 1 here. And performing that same operation on the constants on the right-hand side, we have a negative 4 times negative 4 is positive 16. Adding that to our negative 13, we have a positive 3. So in our last step, well, we have almost exactly what we want. I have now 1s on these diagonal entries, and I have 0s almost everywhere else except for these last 2 entries in my third column. So now my first column, or first 2 columns for x1 and x2 are exactly what I want. So now we're going to move to this third column, x3, to put it in the form that we want. And we see that to kill off this positive and negative 1 in my first or second row, I can make use of the fact that my third row already has a 1 in that third spot. So to kill off the negative 1 in the second row, I could just add row 3 to that second row. So this would be equivalent to the matrix we get by taking row 2 and adding row 3 to it. So our last row, we are not changing. We still have 0, 0, 1, 1. Our second row is now 0, 1, 0. And when we add these constants, our negative 4 plus 1 gives us a negative 3. And In our last step, to kill off this positive 1 coefficient that we have in our first row, last column, I could just subtract the positive 1 that I have in that same column from the third row. That is, take row 1 minus row 3. So let's write the operation we're performing. Row 1 minus row 3. So that leaves me with a first row of 1, 0, 0. And then performing that operation on the constants, I would have 3 minus 1 is 2. So once I have this matrix in the form that I was looking for, I can immediately read off my solution. My first row tells me that x1 is equal to 2. My second row tells me x2 is negative 3. And my third row tells me x3 is 1. So here we have, again, one solution, namely the point 2, negative 3, 1. And again, we could think about this geometrically as representing the point of intersection of all three of the planes whose equations are given in the problem statement. Okay, so let's look at another example. In this next one, the exact same sort of problem. We're asked to solve the following linear system. To do this, we could write it as an augmented matrix and perform Gaussian elimination. In general, that's one of the easiest approaches to solve these linear systems. So let's take a look here. We have, for our augmented matrix, the first row as 2, negative 1, 3, 3. For our second row, we had our second equation. We had 2x1 plus 1x2 plus 4x3 is equal to 4. And our last equation was 2x1 minus 3x2 plus 2x3 is 2. So again, I want to try to transform this into this coefficient matrix A into a matrix where I have 1s on these diagonal entries and 0s everywhere else. If I can get it to that form, then I immediately can read off what x1, x2, and x3 are. So again, if we proceed column by column to do this, well, for my first row, x1, I have a diagonal entry of 2. I know I'd like to try to get it down to a 1, so I could maybe take half of my first row, but then I'm going to introduce some fractions for the other entries in that first row. So let me avoid that for now. But I know for the next two rows, for that first column, I want to have zeros. Now we see here that in the first column, all of our entries are 2. So to kill off the entries 2 in those second two rows, I could simply subtract the first row from them. That is, take row 2 minus row 1. So I'm going to leave my first row alone. I still have 2, negative 1, 3, and 3. Now if I subtract the first row from the second, I have 0. 1 minus the negative 1 gives me 2. 4 minus 3 gives me a 1. And 4 minus 3 is again a 1. Now in my third row, again, if I subtract the first or second row from it, let's see what we have. So I could take my third row and subtract from it either row 1 or row 2, since they all had coefficients of 2. So for this one, let's stick with the first row. I'll take row 3 minus row 1, which would give me 0. Negative 3 minus my negative 1 would give me a negative 2. The 2 minus 3 is a negative 1, and 2 minus 3 is a negative 1. So at this stage, I've reduced my second two rows down to two variables, just in terms of x2 and x3. And you might notice right away here that the second and third rows are identical. One is just the negative of the other. So one way that I could try to simplify in my second column is to try to eliminate this -2. Let's see if we can make this into a 0. Now an easy way to do it here is to use the row directly above it. If I add row 2 to row 3, then I get the 0 in that spot that I'm looking for. So here, we're going to take row 3 and add row 2 to it. So my first row is still the same. I have 2, -1, 3, 3. My second row I'm going to leave alone. I have 0, 2, 1, 1. And then in my last row, I have 0, 0, 0, 0, because the second row was just the negative of my third row. So when I add them, I get a row of all zeros. So let's recall what this tells us. Anytime that we obtain a row of all zeros, we are referring to the equation 0 is equal to 0, which is the trivial equation. It's true regardless of how I choose my variables. So in this case, we have infinitely many solutions of our system, since one of the equations is always going to be satisfied. And to classify the solution set, in the case that we have infinitely many solutions, we need to introduce a free variable. And again, I had mentioned in the first part of the lecture that the typical choice for your free variable is the last variable. In this case, we were working with x1, x2, and x3. So we might choose x3 as our free variable here. Now, let's see if we could simplify our system a little bit further before we introduce that free variable. So one way that I could simplify a little bit further here is to try to kill off this 3 coefficient in my third column. Now we might say, well, typically we would work with the second column first, so maybe I want to turn that 2 into a 1, which I could do by dividing the second row through by 2, but again, that introduces fractions. I could add the first row to the second, and that would give me a 1 right there, but then that would make this first entry a 2 instead of a 0. It would undo my earlier work. So instead of introducing fractions or sort of moving backwards, let's move directly to our third column and see if we can kill off this coefficient of 3. So looking at the coefficient directly below it, it is a positive 1. So to kill off that 3 term, I could take my second row, multiply by a -3, and add it to my first row. Or equivalently, take row 1 and subtract 3 times the second row. So that gives us a first row of 2 minus 0, which is 2. I have a -1 minus 6, or -7. And then my 3 minus 3 gives me the 0 that I wanted there. Now, performing that same operation on the right-hand side, I would have 3 minus 3 is 0 there. And my second row I'm leaving alone. We've got 0, 2, 1, 1, and still our row of all zeros. All right. So at this stage, we can introduce our free variable, or we could try to simplify a bit further here. If we want to force these first 2 diagonal entries in our first 2 rows to be 1, Well, we would have to multiply our first and second row through by 1/2 and introduce some fractions. So let's say that we want to go ahead and proceed that way. We could say this is equivalent to the system we get by taking half of row 1 or half of row 2, and let's see what those rows become. Our first row is then 1, -7/2, 0, 0. Our second row is 0, 1, 1/2, 1/2, and our third row is still a row of all zeros. So at this stage, we could go ahead and introduce our free variable. There's not too much more that we could do to make this a simpler system. Sticking with the convention that we let our last variable, in this case x3, be the free variable, well, let's make our choice for x3 some constant number. Let's denote it as t. So let's say x3 will be equal to t, will be a free variable. So looking at our second equation, I can solve for x2 in terms of x3. My second equation tells me that 1x2 plus 1/2 of x3, so that would be half of t, is equal to 1/2. So solving for x2, I have 1/2 minus 1/2 of t. And to get x1, I could look at my first equation, or my first row in this matrix. I have x1 minus 7/2 x2 has to equal 0. So that is 1x1 minus 7/2 of x2. Now x2 was given by 1/2 minus t over 2, and that has to equal 0. So we find then that x1 is equal to positive 7/2 of 1/2 minus t over 2. So x1 is then equal to 7/4 minus 7/4 times t. So here we have infinitely many solutions, and we would say that the solution set, that is the set of all possible solutions, would be the set of all points where x1 is 7/4 minus 7/4 t, x2 is equal to 1/2 minus t over 2, and x3 is equal to t, such that t was free to be any real number. So this would be our solution set. Here again, it defines a line in 3 dimensions. So these 3 planes intersect in a line which consists of infinitely many points. Hence, we have infinitely many solutions here. So in our last example, we will illustrate how this process of Gaussian elimination might be used to determine what the solution set of a linear system might look like. So we'll look at some problems that are somewhat similar to what we considered in the first part of the lecture, now making use of an augmented matrix. So in this last example, we have a problem that's pretty similar to some of your homework problems from section 1.1. We are asked to determine the value or values of the constant h, such that the matrix given here is the augmented matrix of a consistent linear system. So here again, a little comment about notation. The notation that's given here is what they use throughout the textbook and what I'll continue to use in the notes. The way that I would prefer to write this matrix is by using a little vertical bar to separate that last column vector from my augmented matrix. So really, this first matrix is our coefficient matrix A, and then we have a column vector B on that right-hand side of the vertical line, which is expressing the right-hand side of our equation. So really, we could think about this as representing a linear system of the form 2x1 minus 3x2 is equal to some constant h, and negative 6x1 plus 9x2 is equal to 5. So here we are asked to determine, well, what are the values of this constant h, which is the right-hand side of our first equation, such that the system represented by this augmented matrix is consistent. So what does it mean to be consistent? Again, that means that it is a linear system which has at least one solution. That is, we have infinitely many solutions or exactly one solution of our system. So to determine that constant h, well, we can perform Gaussian elimination on this augmented matrix. We had the matrix 2, negative 3h, and negative 6, 9, 5. So in order to simplify our coefficient matrix A, we could proceed column by column. So my first step here might be to try to kill off this factor of negative 6 in that bottom left entry. So one way that I could get rid of the 6 here, looking at my first row, I had a coefficient of 2, so I could multiply it by 3 and add to the second row. So here, this would be equivalent to the matrix that we get by taking row 3 and adding to it 3 times the first row. Row 2 plus 3 times row 1. So let's see what we get. Our first row is the same. We have 2, negative 3h. And in our second row, we would have a positive 6 minus 6 is 0. A negative 9 plus 9 gives us 0. And performing this operation on the right-hand side, my second row, we had 5 plus 3 times h gives me 5 plus 3h. We don't know what h is yet. Now, in order for this system to be consistent, let's think about what has to hold. Our second equation here says the following. 0x1 plus 0x2, so that is 0, has to equal 5 plus 3 times h. Now, the only way that that second equation can hold is if our constant, 5 plus 3h, is indeed equal to 0. So now we can solve for h. We have 3h would have to equal to negative 5. So h would have to equal to negative 5/3 in order for a solution to exist. Otherwise, our second row would be an equation of the form 0 is equal to a non-zero constant, which would be inconsistent. So here we can say that our system is consistent provided that h is equal to negative 5/3. So in this last example, we have a variable other than x1 and x2 in one of our equations, and we have to come up with restrictions on that variable in order for our solution to be, or for our system to have a solution. So you've got some problems on your section 1.1 homework that are very similar to what we've considered in these lecture notes, where we can solve these linear systems by expressing them in terms of augmented matrices and performing Gaussian elimination. And this process can be a little bit time-consuming and tedious, but it is worthwhile for this course to get a lot of practice performing Gaussian elimination, because we'll see that this process will be used throughout the course and has some really nice applications. So it's worth it to take the time to practice these problems early on in the course. It'll make your work much easier when we get to later chapters.